water condensing on saran wrap or, a plastic dish or in a water bottle, and you see these sparkly colors. I'd seen this many times myself and never given it a second thought.
Much of Lauren Zarzar's work examines closely the everyday phenomena that you might not necessarily think about, but lead to some fascinating discoveries in chemistry. Those discoveries not only landed this Penn State Assistant Professor of Chemistry on the Chemical and Engineering News' 2019 Talented 12, a list of brilliant young scientists taking on some of the world's toughest problems with clever chemistry, but also led to her work being featured on the cover of Nature, which is not something many scientists can claim. In episode 5 of this Science with a Twist series, Bringing Chemistry to Life, we speak with another member of the Talented 12 about their work and trends in their field. I'm your host, Paolo Braiuca, Senior Manager of Global Market Development at Thermo Fisher Scientific. We began by asking Dr. Zarzar about her background and what took her to her current role.
I would say that my path in chemistry started in high school. I've always loved science ever since I can remember, but I was introduced to chemistry as the field in my courses in high school, and ever since then, I've loved chemical and material sciences. When I was younger, I thought I was going to do nanoscience and study carbon nanotubes and these sort of materials. I ended up going to graduate school and doing something that I totally knew nothing about, working with hydrogels and stimuli-responsive materials. I just kept an open mind. Whatever was exciting to me, that's what I pursued. And that's ultimately led me to where I am now, where I'm really excited to think about how do we design materials that are adaptive, responsive, that can interact with their environment and exhibit more lifelike properties. And that's what really gets me excited in my day-to-day research.
So, if I read your research lab's website, the way you summarize your research links into what you just said. So you define it as design, synthesis, and integration of materials for adaptive microscale systems. I think this deserves a bit of an extra explanation.
Sure. Big picture, we're excited about developing materials that exhibit more responsive, adaptive, or lifelike characteristics. And so sometimes we say that the work that we do is bio-inspired. Living organisms, in a sense, are sort of the most adaptive functional materials that exist. Totally different from the materials that we design and engineer, which are mostly static. I think the next generation of materials that we create are going to have more of those adaptive responsive properties similar to living organisms, where their functions and their properties change based on their environment and their circumstances. Typically, when we think about how to design those sort of materials, you can't just use one chemical. You can't just use one individual material. Just like a living organism, which has all these functioning parts and materials that work together to create something that has functionality greater than the sum of the individual parts. I think we have to think that way in terms of materials design as well. And so that's where the materials integration part comes in. Thinking across length scales, different types of materials, hard materials, soft materials, and how all of these things work together to create a system that is responsive and adaptive and has this next level of functionality.
Is understanding the microscale really the key to develop microscopic properties of material that can be useful on a day-by-day basis?
Yes, this is one of the things that gets me really excited about the intersection of chemistry and material science, is thinking about how the molecular to microscale impacts macroscale properties. This is something that we think about a lot in our lab, because we're working with chemicals where obviously you have to think about reactions and intermolecular interactions and assembly on a more molecular scale, but then you have, say, a droplet or a polymer or something that has a microstructure to it. And those interfaces and interactions on the microscale, the geometry and how those materials are organized on the microscale then again impacts the macroscale. So it's really thinking about those length scales and those interactions spanning molecular, micro, and macro scale. That's something we think about a lot.
It is very interesting. And if I look at work that won you the consideration for the Talented 12 and the cover of Nature, by the way, it seems like there's also the need to understand some fundamental phenomena that happen at the microscale that some people might have completely overlooked in the past?
Some of the most exciting discoveries, I think, are going to be these really simple things that maybe people have just overlooked across the years, and opens up totally new directions that you could go in your work. Speaking more directly to the work you were mentioning that was highlighted in Nature, this was about how structural color is generated. And, people always thought that structural color and interference colors, you would design a material that had some sort of periodicity on the scale of the wavelength of visible light so that you would get interference and you'd get color. And here we are making color in microscale materials that are orders of magnitude larger than you would normally think to create a material that has these colors. And in liquids, just microscale droplets that people see every day. Thinking about things that are commonplace, but just looking at them from a slightly different way, I think we can learn a lot.
It was really mind-blowing to me to think that, the specific examples that you studied in that piece of work were things that most of us have actually experienced on our normal lives, like condensation of water droplets on a plastic container, right? And the sort of coloration, sort of rainbow effect that you can see on that surface. And no one really understood what that was coming from. What inspired you to look into these effects, and how did it come to you that this might be something different from what people expected it to be?
I myself have seen this same effect, water condensing on saran wrap, or a plastic dish, or in a water bottle, and you see these sparkly colors. I'd seen this many times myself and never given it a second thought. But in the context of our research, so we were making these droplets that were on the sort of 50 to 100 micron scale. And we were making these droplets so that they were all the same size. And just collecting them in a petri dish and noticing, again, these colors. It was accidental. It's one of those moments in the lab where you see something totally unexpected and you're sort of caught off guard. It's like, well, why does it have these colors? All these liquids are clear. They're 50 microns, so they're orders of magnitude larger than the wavelength of the visible light. There's no nanoparticles, there's no dyes. Where's this color coming from? Based on my very fundamental, basic understanding of optics, at the time, I was, very surprised to see iridescence, meaning that the color actually changed depending on the direction that we're looking at these droplets and the lighting conditions, which to me signaled structural color. And it was just, these droplets were just not consistent with the picture I had in my head of, diffraction gratings and thin film interference and photonic crystals. These are the kind of structures that generate interference colors. And that's really what led us down this path, was just seeing something that seems very simple, but I just had no, explanation in my head for what was causing this.
So what was the expectation? So if I understand it correctly, droplets that you were observing were big enough not to be expected to produce any sort of coloration. Am I right? The reality was that you being able to observe that these were actually generating a color under certain specific light conditions meant that there was a different sort of mechanism that was never understood or never observed before properly.
Yes. So we were able to create color in a material that nobody would think to create color in before. Now that we know that we can create a color using a microscale liquid, opens up new directions for us to go in terms of both the science and engineering and material development.
Can you go a little bit more into the physical chemical characteristics of this coloration?
So to create structural color, typically it's caused by light that interferes. The wavelengths of light either are constructively, destructively interfere, depending on the paths that they take while bouncing around in a material. And usually you use a geometry such as a diffraction grating. I'll use this as an example, like the back of a CD. Turn the CD at different angles, you see different colors. These are coming from these very small grooves on the surface of the CD that have periodicity on the scale of the wavelength of visible light, somewhere in the 400 nanometer to 1 micron range. And the light bounces off of these interfaces. It experiences a different path length, so it travels a different distance based on how it bounces off these materials. And the light is then allowed to interfere, and that's what gives you the color. Typically, to generate structural color, you need these periodic geometries on the scale of the wavelength of visible light. So the CD, thin film interference, like an oil slick in the parking lot, these all have these nanoscale periodic geometries. Now take these microscale droplets. It's just one interface. Imagine a hemisphere of a clear water droplet that is 50 microns across. It is an interference color that we're getting from light interacting with these droplets, but the way that the light bounces around and interacts with this material is very different. So the interference mechanism in the droplets is that light bounces by total internal reflection at the air-water interface. So total internal reflection is essentially, you can think of the interface as a mirror for certain light incidence angles. So at certain angles of the light hitting that air-water interface, the light will bounce like it's at a mirror surface, and it can bounce several times around this concave interface of the droplet. And light that hits different positions of that interface will bounce different numbers of times. So you've got light that has many possible different trajectories around this concave interface. When it exits the droplet, this light has experienced many different paths, many different trajectories, so some parts are in phase, some parts are out of phase, and you get constructive and destructive interference. So that's where the color comes from. It's still an interference mechanism, but the way that you generate those path length differences is in a droplet that is very, very large compared to the scale of the light itself. It's something that people don't usually think about when they're generating these structural color materials.
And so if you're able to control the geometry of this surface and the curvature of this concave surface, for instance, then you are potentially able to control the color characteristics of the interface.
Yes, that's correct. And that draws in some of these ideas of the dynamic materials as well. Because now if you can create the color using a liquid droplet, then you can change the curvature of the droplet. You can change the size of the droplet. That allows you to dynamically tune the color and the optical properties of the surface.
Does this happen only on the liquid-air interface, or can you use different types of surfaces and interfaces?
You can use many different kinds of interfaces. So yes, the example I gave was probably the simplest case of a water droplet in air, but we have observed this phenomenon at many different interfaces within oil droplets in water. We've observed this in solids as well. So we can create solid surfaces that you can have, a solid domed surface in air. You could have a interface between two solid materials of different refractive index. So there really isn't any limitation on the material properties of the interface itself. What's most important is the geometry of that interface and the refractive index contrast at that interface.
Are there certain type of materials that are more prone to generate this effect, or is it just a universal property of potentially all chemicals?
It's pretty universal. I've also talked mostly about curved surfaces, and liquids are great for curved surfaces. They'll naturally form wonderful interfaces to use for optics, but you're not limited to curved interfaces. And so if you want to explore polygons and other funky shapes that will also give this effect too, then you want to use solids so that you can structure them in different ways to tune the interference. But it's pretty universal. We've observed it in so many different situations. I think we're just really at the tip of the iceberg in learning how to control it, actually. And I'm very excited for the directions of this project.
It seems to be potentially opening a lot of opportunities, but the systems you have described, like water droplets condensing on surfaces or emulsions, they tend to be static systems. I believe that the real excitement might come to being able to control dynamically the characteristics of the interfaces. Are you able to do that already?
We have shown examples where you can use droplets to controllably pattern the colors. One way we do this is by creating a droplet that has two different oils in it, and the color actually comes from the interface between the two oils. And based on the surfactants, basically soaps that we add to our oil droplets in water, we can tune very specifically the shape of these oil droplets, and therefore we can tune the color. So we've actually demonstrated that you can use fully liquid droplet systems to create structurally colored images by patterning the shapes of these droplets.
What are the potential real-life application of this finding?
So some of the more immediate applications that we're looking at are more so using this effect in solid films. Structurally colored or iridescent materials are actually already used in a number of applications, such as in security and anti-counterfeiting applications, holograms, color shifting inks. Plus they also have just aesthetic use, car paints, coatings, makeup, and nail polish. There are a lot of already commercial uses for color shifting or structurally colored materials. And given that we have a pretty unique way of controlling light by using these different geometries, one direction that we're looking towards is, can we harness this effect in commercial materials like paints, coatings? So that's probably the most immediate application that we're interested in. I still think there's a lot of more fundamentally interesting work to be done with liquids. Liquids are a little bit harder to harness as materials still. We have to get a little bit better at being able to control them, because you do have to very precisely manipulate the positions, the curvature of the interfaces, the stability of the droplets. But in terms of dynamic materials, I think using liquids, for some sort of liquid display or liquid droplet sensor, for instance, could be a very interesting direction to go.
And Lauren, I'd like to move on to one other slightly different line of research that you're carrying on with your group, which is laser fabrication methods. It seemed to me like 3D printing at a nanoscale. Can you explain what this is about?
In this research, we're trying to use a laser to allow us to simultaneously synthesize materials and pattern and deposit them together on the microscale in a 3D printed structured architecture. 3D printing obviously has become a really big hot topic of research now. Most 3D printing is still on the macro scale, starting, 100 micron scale is the lower end. There are some newer technologies now, multiphoton lithography, for instance, that does let you get down to the, micron to submicron scale for 3D printing. But there is a scale in 3D printing on this sort of 1 to 10 micron scale that's still very difficult to access. It's very difficult if you want to pattern many, many different materials together on that length scale. It's exceedingly difficult using traditional manufacturing and patterning methods. So one of our goals is to be able to develop methods that allow you to pattern and integrate both organic and inorganic materials together on this sort of 1 to 10 to 100 micron length scale.
Can you tell us a bit more, what are these materials you're working on? You mentioned organic and inorganic material. What's the chemistry behind it?
So a lot of our more recent work has been on the synthesis and patterning of metals and metal oxides, composites, alloys, and mixtures thereof. And how we synthesize these materials is we're actually taking a very old and well-known field of chemistry, solvothermal synthesis, where you have a flask full of solvent and some chemical precursors. Maybe you throw in a reducing agent, you heat it up, and you get inorganic nanoparticles. But then you're left with this flask full of the nanoparticles. They're not patterned. They're not, you have to go through all of these subsequent steps to purify it and pattern the material. So we're trying to take that chemistry, that solvothermal chemistry, and shrink it down to the microscale. The focus of our laser is basically serving as a tiny reaction flask where we're heating up our precursors in solution. We're only heating them up at the focus of the laser. We're inducing chemical reactions just at the laser focus, simultaneously synthesizing those nanoparticles, sintering them down onto the substrate, and then we move the laser. We're basically drawing with the laser beam, and as we move it, we deposit these inorganic materials like the metals, metal oxides, onto the surface. And then if we want to deposit a different material, then we just rinse out the solution, put a new one, and write again. We have these aspects of the chemistry and the synthesis. You can switch out whatever precursors you have, but then you can also pattern them together.
So what you're saying is that potentially you can design materials at the microscale where you use a sequence of different reactions starting from different building blocks and having actually localized products that are positioned exactly where you want them to be positioned. And then overall, this can create a macroscopic properties of a material, completely new and never seen before, that are unobtainable with traditional synthetic methods.
We're still in the early stages of actually finding out what are the material properties of the things that we synthesize. We're still working on that. But the idea would be that you can integrate materials together in ways that would be very difficult otherwise, right? And we spoke earlier about how materials integration is really important for these next generation devices and materials platforms, for instance. And so, I believe that if we can develop fabrication methods that facilitate our ability to integrate materials in new ways, even if they're old materials, but if we can integrate them in new ways that people hadn't been able to access before, that in and of itself, I think will enable new technologies.
You seem to be really visionary in your approach to research. So you seem to be having a sort of end goal in mind from the beginning. Do you foresee, even in this case, some potential real application once the fundamentals are in place?
Sure, I can give you a few examples of actually some of the directions that we're working on right now through collaborations here at Penn State. Some of the directions that we're looking at are for sensing applications, so gas sensors, biosensors, as well as catalysis. So for example, metal oxide gas sensors, very common, already used commercially. The problem is they tend to not be very specific. The metal oxide either gets oxidized or reduced, and it's hard to identify what the specific gas is. If you have a mixture of gases, potentially not very useful. You can't get away with just using one metal oxide. But what if you have a dozen different metals and metal oxides that you know how they respond to different gases, and so you can use this in a combinatorial way to deconvolute the response of a mixture. The challenge is then, how do you pattern all of these dozens of materials together on a microscale footprint? So this is an example of where I think this technology could be really beneficial, because now we can directly pattern all of these different nanostructured materials on the microscale, integrate with electrodes, integrate with heaters, and potentially enable a new sort of device platform.
So you seem to be working at the forefront of a lot of exciting innovations here, and the technology you're developing can enable the production of completely innovative materials going forward. Is there any specific technology that is coming to maturity or has come to maturity lately that is enabling you to progress in your field of research?
Yes, and actually that technology is actually multiphoton lithography, which is not a new field, right? People have known about how to pattern polymers using multiphoton lithography previously, but what's new is its accessibility in a commercial platform. And I guess I should define what I mean by multiphoton lithography. What is this tool? And the idea is that you use a laser. And again, the focal point of the laser defines a reaction spot, a very small spot where you're going to generate a polymer. And as you move that focal point around in 3D, you can basically draw and create 3D structured polymers with nanoscale resolution. So this is a tool that enables us to basically 3D print polymers on the scale of a couple hundred nanometers, all the way up to millimeter scale. With very high precision, we can just arbitrary structures. And so this is a laser patterning approach, but we're using it now to create new optical coding. So we're designing concave interfaces that generate color by the structural color mechanism, but we're making funky shapes. So we're not using spheres anymore. We're getting creative with the different interfaces so that we can control how the light bounces around in these cavities and use that as a way to tune the interference in the color. And we would not be able to do this if this multiphoton lithography tool did not exist. And also, if it didn't exist on the commercial scale, where now we can actually start to pattern things, not just one or two structures that takes us 10 hours to print, but actually, can we make these on the centimeter scale, inches, meter? Like, this is starting to become a commercially viable approach for patterning materials, which I think will be very enabling for some of our future investigations.
It is fascinating to see how you can converge lines of research that seem to be very different by keeping an open mind towards available technologies and a multidisciplinary approach to your research. And I think it's fair to say that some of the most exciting science is coming from merging disciplines together, or maybe just, if you want to crack a joke, at the interface between different disciplines. Would you agree?
I definitely agree. I think the latest and greatest innovations are going to come from people thinking at those boundaries between the traditional disciplines. There's actually a creative thinking tool, if you will, that I try to be aware of and get my students to think about too in their brainstorming, which is this idea of forced association. Taking two things that people would never put together and coming up with ways in which they're related or ways in which you can make them related. And it forces you to be cognizant of this fact that in order to really be an innovator, you've got to think about ways and see things that nobody else has seen before. And one way to do that is by taking very different, disparate fields and ideas and putting them together.
Is it what you mean when you said during your chemical and engineering news presentation with training the creativity?
Yes, so that is one way in which I think you can train or at least be more metacognitively aware of how you think about problems and how you brainstorm and how you approach problem solving. I know there are people that disagree with this idea that creativity can be trained. I think that there's not really a consensus on this that I'm aware of. Some people think that creativity is innate. Some people think that creativity is something that you can learn and train. I tend to fall into the second group. I try to have a growth mindset when it comes to this. And it's also about being aware of limitations that you're putting on yourself that you don't even intend to put on yourself. I think because we're scientists and we're so used to thinking within boundaries, we sometimes put boundaries and rules on ourselves in our problem solving that actually don't exist, and that restricts us in our thinking. And so just being aware of that, I think, will help you become a more creative thinker.
What are some of the technical or personal challenges that maybe creativity is helping you to overcome?
Science is full of what seem like dead ends. You do so many experiments, you feel like they're failing, and it can be very discouraging. So this idea of keeping an open mind and really enjoying the process of, the scientific method, and I feel like I'm stuck here, but maybe what I'm doing is I'm just confining my thinking too much. What if I just take a step back and go, okay, what I'm doing isn't working. Let's try something, way over there. It opens up entirely new possibilities, and it takes a discouraging problem and it makes it an exciting new opportunity.
And thinking about things that can enable you to do your job properly, do you think the chemical market at the moment is in the right place to support your group with your research? Do you find the right quality of materials or the right tools that you need in there? Or do you think there's anything the suppliers can improve?
So for the most part, yes. I mean, when I think about how amazing it is that I can log onto my computer, search through millions of products, order them, have them delivered to my door, without the industry, we would not be able to do any of this work, right? So it is really amazing. Are there things sometimes that we want that we can't get or that are too expensive, et cetera? Yeah, there definitely are. I think one challenge is that as a scientist trying to work, at the forefront of new technologies and new fields, is that some of those materials are not commercially used yet, or those techniques have not been developed, etc. So you got to make them up yourself. Sometimes we can, sometimes we can't.
But that's the right approach, Lauren, certainly. So as we come to the end of our chat, which has been very entertaining for me so far, there's a question I'd like to ask, which is, now that you are still a young researcher, but you have accomplished a lot already, and you certainly have a bright future ahead of you, what is the one piece of advice you pass on to a young colleague, a young chemist or a young scientist just starting in their career?
Don't focus too much on the end outcome of the experiment or the research. And I alluded to this a little bit earlier, I think. If you can love the scientific method, coming up with a hypothesis, designing your experiments, testing, and learning something new, that at that moment in time, you're the only person that knows that, and that enjoyment of discovery, I think that's what's going to keep somebody coming back, day after day to want to be a scientist or an engineer and make it their career. If you focus too much on the end outcome, I think it can be very discouraging, because a lot of the experiments we do don't turn out the way we hoped. We still learn things from that, but a lot of the time you don't accomplish what you want, or things don't work the way you want. And that's not a bad thing. That's just the way it is, but it can be discouraging. And so focusing instead on the joy of discovery, the joy of applying the scientific method, that's what I think is really exciting about science, and what gets me motivated every day to work with my students and design our research program. And it gets you through all of those tough things that don't necessarily work, and keeps you focused on enjoying the scientific method and process.
That was Dr. Lauren Zarzar, Assistant Professor of Chemistry at Penn State University and one of Chemical and Engineering News' Talented 12. Thanks for joining us for this episode Bringing Chemistry to Life, a Science with a Twist series. We'll bring you more conversations with the Talented 12 every other week. For new episodes, subscribe wherever you get your podcasts, and you can visit labchemresources.com for special access to our guest profile sheet, which has more information about Dr. Zarzar, recent publications from her group, and her content recommendations. This episode was produced by Matt Ferris, Gabriel Orama, and Emma Jean Weinstein.